started. So we were talking about robust estimation on Friday's class. So we talked about robust Kalman filter. Today we'll continue our discussion. One of the things we talked about on Friday was this estimator called Stahel-Donoho robust estimator. So there are many ways by which you can do robust estimation in a dynamic system. So remember, we have xt plus 1 equals to axt plus wt, and now I'm going to make a slight change. So we have n sensors, and each are measuring YTI, and so you can write a Kalman filter for each sensor to get x hat t given t comma I. So now the question is, I'm driving a car on the road, so that's my state. My position and velocity would be my state. Or there are other cars on the road as well, so there may be cars, trucks, people, pedestrians, and so on. Each of their position and velocity would be the state of the system. So you have like a very high dimensional state space here that you're observing, which is people who are outside the vehicle. And then you have 3 cameras, 2 lidars, 3 radars, and so on and so forth. So you have n such sensors. Each of the sensors is sensing the environment, and you get the observation. Based on the observation, based on the noise statistics of those sensors, you come up with a filter. You run a Kalman filter for every sensor, and you come up with an estimate. And based on all this estimate that you have made, based on the observation, I want to map it to the estimate of the state, overall estimate of the state, knowing well that in fact some of these sensors might be attacked. So now the question is, how do you come up with the estimate of the state given that some of the sensors might be attacked? Okay. So this particular problem is a very important problem, but unfortunately there is no single technique that has emerged as a winner. This topic has been a subject of intense investigation from 2010 onwards, 2008, 2010 onwards. There are probably hundreds of papers on this topic by now, and there is no single clear winner. Like, this is a very good way of coming up with resilient estimation of the system. So what do I mean by resilient estimation? So resilient estimation means you are running this estimator and an attack happens, and the estimator is resilient, which means that even though the attack is happening, so when the attack is not happening, it is coming up with the right estimate. When the attack is happening, then also it is coming up with the right estimate, as long as the attacker is bounded in some fashion. So the resilient estimation just means that you run the resilient estimator, and whether attack is happening or not happening, you pretty much get the get a very good estimate of what the state is. So Kalman filter is not a resilient estimator, because Kalman filter, the underlying assumption is the noise statistics is known. And the problem with attackers is you don't quite know what the noise statistics is. All you know is the attacker can maybe attack only 2 cameras, but the LiDAR and the radar is safe from the attacker. Or the attacker might attack the LiDAR, but the cameras and the radars are safe from the attacker. So now the question is, how do you aggregate all of these estimates in order to get a true estimate of the state? So one simple method that people have studied is the following method. So you do the clustering. So step 1 is cluster this x hat t comma t given I, and step 2 is pick the cluster mean of largest cluster. How many of you have studied clustering before? No? So clustering is the technique wherein you pick so this is my Rn, and this is my x hat t given t comma 1. This is my x hat t given t comma 2, x hat t comma 3, and so on. Okay, so what we are doing here is called clustering. So we look at the estimate from each of the n sensors and we cluster it. So clustering means we basically there is an algorithm to do clustering. It basically puts every point in a specific subset. So there is a subset of points that are close to each other. There is another subset of points that are close to each other. And so now the clustering algorithm will look at this particular value, this vector, and it will tell you, okay, it belongs to cluster 1 or cluster 2. So this is my cluster 2 and this is my cluster 1. There are inbuilt packages to do clustering, so I don't want to get into the clustering algorithm, but basically it tells you which points are close together, and so it puts them in one specific cluster. So all the points that are close together is in one cluster, all the points that are close together is in another cluster. And then the step 2 is saying that I'll look at the cluster which has the largest number of points. So this particular cluster has 1, 2, 3, 4, 5, 6, 7, 8. So this one has 8 points. So remember, these are all the estimates from the n sensors that I'm clustering. So I have 8 points here, and here I have only 4 points in this particular cluster. So I look at this cluster 1 has 8 points. These are all close together. So I'm going to take the mean of each of these estimates, and I'm going to set my x hat t to be that particular estimate. So the mean of all of these estimates. So I'm going to discard all of these estimates. So estimates from cluster 2 will be discarded, and the mean of the estimates of cluster 1 will be taken as x hat t. So that's one of the simple algorithms for doing resilient estimation. The complexity here is doing this clustering. So if X is a small dimensional 5-6 dimensional object, I think clustering is very easy. If X hat becomes 100 dimensional object, then clustering becomes very difficult. Okay, so just something to keep in mind. Clustering is very simple in small dimensions. It becomes very complicated in high dimensions. Also, clustering becomes very simple if you have fewer number of sensors. It becomes very difficult if you have very large number of sensors. When do you have very large number of sensors? Any idea? So, I don't think you probably would know, but many space agencies across the world, they are trying to put, thousands of satellites in space, like microsatellites in space. So they'll be like, I don't know, satellite which is of this particular size, a small size like this big, and then they are going to put it in the space and they are going to measure random things on the Earth's surface or maybe deep space. So that's a situation where you have thousands of sensors, each of them sensing something about the state of the system. And those are the cases where if there is an attack on those clusters, then you need to figure out which one is the best, which one is giving you the best estimate of the state of the system. Okay, I think even this building, like the number of temperature sensors, so temperature is one dimensional, so X hat will be one dimensional, but the number of temperature sensors in the building would be of the order of 100. So there is a complexity in clustering and then taking the cluster mean of the largest cluster. So something to keep in mind that this may not be the best algorithm depending on the size of the state space. Okay, so that was the first algorithm. The second algorithm that people have studied, my X hat T is argmin of X hat of JT of X hat, and JT of X hat is YTI minus CI X hat transpose sigma VI inverse I'll put some lambda 1 and plus lambda 2 X hat minus AX hat T minus 1 PT given T inverse X hat minus lambda 1 and lambda 2 are positive numbers. Okay, so here what we are doing is we have all these observations at the current time step. I'm going to run a Kalman filter based on all the observations I have made so far, and I'm going to come up with this matrix of this is the covariance of the x minus x hat at time t given all the observations until time t. So, I am going to compute this matrix. I am going to take the inverse here. I know what the estimate at the previous time step was. So, I am going to keep that estimate here, and then this is the estimate that is unknown. So, I am going to put that estimate, the unknown estimate, at these locations, and then by weighing lambda 1 and lambda 2 accordingly, I can come up with this cost function, and I am going to minimize this cost function in order to get the robust estimate of x hat t. So, this one has a lower computational complexity because, as you can observe, this is actually a convex function. So, you can actually solve this problem exactly. If there are no further constraints, you can solve this problem exactly, and you can find out what the value of x hat is going to be. Okay, so that's another algorithm that people have tried with various values of lambda 1 and lambda 2. These are all simple algorithms, but depending on the computational complexity, people have come up with different types of algorithms. So this is the second algorithm I wanted to talk about. Any questions on this? I think it's fairly straightforward. We look at the error. This is the error between the observation and your estimate, and this is the error between the current estimate and the previous estimate based on the past information, past estimate. And you want to trade it off, and you are trading it off by picking appropriate values of lambda 1 and lambda 2. Okay. Yes, yes.
The formula seems like really similar to common filter.
That's right.
But
Except for this lambda 1 and lambda 2.
So the meaning to tune the lambda 1, lambda 2 is like make similar common filter to approach the model more, something like that.
Yeah. That's the ultimate goal. So sometimes you can also put this lambda as a function of I, and so you can trust some sensors more than the others. But that's basically, now we are in an territory where you can come up with an idea, and that could be a good idea for a specific system and a specific attack model. So I'm just covering like what the algorithms are without really going into what the attack models people studied in those papers. Okay. Any question? Okay. So third algorithm is also very similar. So do you remember the weight Wi from the previous class? I think I'll remind you of the weight. So Wi are x hat t given t comma I, and then this function r was given by y. So the function R1 was given in the previous class. So I'm just recalling this particular notation from the previous class. And instead of using y and capital X, I'm now computing the estimate of the current state and then the estimates of all the sensors together. And then your this thing could be, your estimate could be summation Wi x at t given t comma I over summation wi. That's another estimate. And then some people have come up with somewhat more sophisticated estimators based on this particular idea. But the problem with those papers is that the notation is very poorly picked, so I cannot understand what the algorithm is. But here is what my assumption is. This is what the algorithm is trying to do. They have pretty good results, by the way. Like in simulation, everything seems to be working out. But for whatever reason, their notation is very, very badly picked in the paper. So those of you, I mean, I know you have not worked with me, but I am very particular about notation. I get very confused if you don't pick your notations correctly. So my graduate students have to spend 1 year figuring out what is the right notation for the paper. So anyway, so that's why when I come across a paper like this where the notations are not very clear, then it confuses me a lot. But here is what my hypothesis is this paper is trying to do. So it looks at, let me write down a matrix. Let me write down the matrix as ZT, which is YIT minus 1 minus C x hat t minus 1 and then x hat t minus 1 and then Ci. This is y t minus 1 I, yt I minus Ci x hat t x hat t these values are coming from Kalman filter. You assume that there is no attack node and you just run a Kalman filter regularly and you come up with these estimates. Oh, and this is I equals 1 to n. So you stack all of these as a matrix, and so you get a very big fat matrix, and then you come up with a cost function jt, which is a function of this matrix zt and these wi's. And then you minimize to get x hat t. So what they do is they look at these matrices. So these matrices, you have n such matrices here. So you look at these n matrices here. You look at all these wi's that you are getting from here. So you look at all of these wi's, and then you construct a cost function which is based on Huber loss. I am sort of hand waving some things here because I don't quite understand the algorithm, but I wanted to show you that there are people who are working on different ways of solving this problem. So they come up with so Huber loss is used in robust statistics. We haven't talked about robust statistics, but this particular function, actually this function also comes from robust statistics. So anyways, there is a Huber loss, so they use Huber loss in order to construct this particular function, jt, and then they minimize it in order to get the value of x hat t, which is your estimate of the current time step. The cool thing here is actually it is taking previous data and the current data in order to come up with the current estimate. So this is known as a batch processing because you are looking at successive data in order to come up with the best estimate. So you need to have like some data set in order to be able to run this filter. You can't really run it in real time. So the way they implement in the paper is they look at a batch of data, they run this filtering algorithm on top of it, they get the trajectory, then they look at the next batch of data, they do this filtering, and then they come up with the next set of trajectory. So that's how they run the Kalman, the resilient filter or the robust filter for this particular kind of system. And if you write a paper, make sure that you set up the notations correctly and don't confuse me. That's the way to get 20 out of 20 in this particular project, in the project presentation. Okay. Okay, so does that make sense? Any question? So what you can see here is depending on the assumption, depending on the computational complexity you want, depending on the computing power you have on board. So if you are running it on a supercomputer, you can do a lot more computation. If you are running it on a microcontroller, you have to do very minimal computation. You can pick the kind of filter you want, robust filter or a resilient filter you want in order to do a resilient estimation of a stochastic process under attack. Okay. The key thing to remember, the key thing that should be in the back of your mind should be that when you are under attack, this particular vector is no longer Gaussian. Okay, the distribution changes for this particular vector for the sensors that are under attack. So you can have like camera, LiDAR, radar, and only the radar is attacked, or only the camera is attacked, or only the LiDAR is attacked. And under the attack, this particular noise statistics change. And so you want to make sure that whatever estimation scheme you create, make sure that it's very robust or resilient to the fact that this was assumed to be Gaussian. Okay, Kalman filter assumes this to be Gaussian, mean zero Gaussian random variable, and if you depart from that assumption, then the Kalman filter is very bad. And under attack, that's exactly what happens. You are no longer Gaussian with mean zero, and the covariance is also unknown. So that's where all this robust estimation techniques comes into picture. Okay. And if you look at the paper, there are 100, 150 or so papers, each of them coming up with their own resilient estimation algorithm, depending on the problem formulation. So it's a very, very vast topic. Okay, so what have we done in this class? So I want you to go back to this particular figure. So this is your YT, this is your UT, and what is happening in this block? So there are 4 sub-blocks within this block. There is detection, there is robust estimation, there is planning, and then there is control. So all of them are talking to each other. Well, not quite, but detector is talking to planning, robust estimator is talking to planning. Detection and robust estimation may also talk to each other. After things are planned, it goes into the control block, and that sends the control command to the actuator. Okay, so what do we have here? We have actuators, we have air handling units, we have engine, we have complex turbine engines, we have aircrafts and so on, aircraft engines and so on. So there are lots of actuators. It acts on the plant, and then the sensors are supposed to measure the state of the system. So what kind of sensors are there? There is temperature sensor, there is pressure sensor, there is rotation sensor, there is vibration sensor, there is pitot tube which measures the air speed, so airflow speed measurement. So lots of sensors are there, and the sensors are sending information via communication channel to your control block. So in old days, the system will be designed as follows. The sensor is measuring whatever state it is measuring, so the xt will flow in here, and there is no longer detection, robust estimation and planning block. There is only a control block, and the controller will comprise of PID controllers, lead lag controllers, some sort of LQR controllers and so on, and that information will go to the actuator directly. Okay, so there is none of these blocks exist. Then people said, okay, we need lower fuel consumption, we want lower emission, we want better customer experience, we want better, I don't know, something XYZ, better performance. So we need to do some of planning. So what planning does is it looks ahead into the future, what is going to happen into the future, and then based on some prediction about the future, it's going to figure out what is the best control to do at this point of time. So in order to do planning, we have studied adaptive control, we have studied dynamic programming, we have studied robust control, and so on and so forth. There is a whole bunch of planning algorithms that we have studied. That was lecture, I think, 10, 11, 12, and so on, when we talked a lot about the planning algorithms. So we talked about control algorithms, and we also talked about planning algorithms. Then people said, hey, look, you know, there are these communication channels, there are evil people out there in the wild, and they want to attack the system. What does it mean to attack? They can drop the sensing packets that are coming into the system, or they can drop the control packets that are going to the actuator. So as a result of which, we said, okay, if the information is going to get blocked, then we have to come up with an estimation under lossy networks, and we need to come up with control over lossy networks. And so we came up with a planning algorithm, and we came up with an estimation algorithm, so that we can do the joint estimation and planning in order to make sure that the system, the plant doesn't become unstable, and you are doing an assignment on that which is due today. So that's the other part. And then we said, okay, maybe there are going to be attacks, complicated attacks, where the information actually is changed. So it's not like the packet is not receiving, but attacker is purposefully changing the information that is getting fed into this particular block. So now things become more complicated. So now we need to detect if an attacker is purposefully changing the information or not. So we all talked about Ocean's 11, and how the people were spoofing the camera feed to the security, and the security was not able to detect it. So they were spoofing, they were sending wrong information to the security, so we need to detect it. And so we understood different algorithms for detection. We talked about dynamic watermarking algorithm, we talked about QSUM score, chi-square test, and so on and so forth. All of those are detection schemes. And then we said, you know what, if they selectively pick some of the sensors and then they change the reading of those sensors. So I have LiDAR, I have radar, I have camera, I have airflow measurement, I have temperature sensor, I have pressure sensor, and the adversary comes and only changes the camera sensor by just flashing a light in a visible spectrum. So the camera sensor is completely saturated, as a result of which camera is giving some random information. So they have attacked a specific sensor, but other sensors are unharmed. So visible spectrum light doesn't influence LiDAR, and it doesn't influence radar. Okay, so you still have some information. So now you need to figure out how to do this sensor fusion. How do I know which sensor I should trust and which sensor I should not trust? If the camera says there is a pedestrian, and if my LiDAR says there is no pedestrian, I need to make a decision whether to stop or whether to continue to go. So then we talked about robust estimation or resilient estimation, which is while the detection is happening and detection is trying to figure out if somebody is tampering with the data or not, I want to make sure that at no point of time I have the wrong estimate of the state of the system. As a result of which I need to do robust estimation. The robust estimation gets fed to the planning algorithm, which is the dynamic programming algorithm or whatever, LQR algorithm. And then it comes up with, this is the action that is optimal action at this point of time based on all the information that I'm seeing right now. And then the controller looks at that action and then sends the control command to the actuator. Okay. So that's roughly how the new generation of systems are being created. And so my ex-PhD student, so he completed his PhD in 2022. He worked a lot on cybersecurity and cyber attack detection for autonomous systems. So he went to GE, and right now he's working as a lead engineer in GE, lead research engineer in GE, and he is coming up with the detection algorithm, estimation algorithm, and the planning algorithm for a lot of sophisticated GE assets. So GE owns, so he's in the energy side of GE, so he looks at wind farms, gas turbine generators, and those kind of engines, complicated engines. So he's going to talk about the work that he's doing back in GE next Monday. Okay, so keep this thing in mind when you listen to his talk, because he's going to refer to this kind of diagram again and again in his talk. So one thing that we have not talked about is localization. So by localization, what I mean is, yes, we can do the robust estimation, but we don't quite know which of the sensors are attacked. So typically localization is done by looking at a pair of sensors and running detection on multiple pairs of sensors. So I have like a camera LiDAR. So I pick a camera and a LiDAR and I do a detection, and then I pick a LiDAR and a radar and I do another detection, and then I do camera and radar and I do another detection. And by looking at which of the detectors are turning on versus which of the detectors are not turning on, you kind of localize the attack in the sense that you figure out, okay, these are the sensors that are getting attacked, but these sensors are not getting attacked. Okay, so localization is just a fancier version of detection where you're looking at pairs of sensors and you're doing detection on pairs of sensor readings. So that's what happens in localization. So he's going to talk about a lot of these things from the point of view of GE, and that's pretty much it. That's the purpose of this course. It was to introduce you to all of these blocks, talk about some of the major algorithms that are used for controlling modern autonomous systems. Hopefully some of you will go to autonomous driving companies. Hopefully some of you will go to GE Energy or GE Aerospace, and you will be designing these algorithms for the rest of your life. and the course will be on YouTube. So no matter when, you can come back to it. Even after you retire, you can come back to the course and you can see what we studied and hopefully implement it in whatever engineering systems you might be working on. So thank you so much. You have been a wonderful audience, and we'll hopefully meet again next year, next academic year. Yeah.